Hello, everyone. Welcome to Math and Beyond and this podcast. Today, it's episode 8, and we are going to talk with Toon about fluid dynamics. I will send him the invite, and I will see you shortly. Hi, Toon.
Well, hello.
Hi.
Hi.
Yeah. Hi. Nice to meet you.
Well, nice to meet you as well. I just had to accept some technical difficulties apparently. So that's always.
Don't worry. How are you?
I'm doing fine. Nice weather outside. It was supposed to rain, but it's still keeping dry, so it's already a good day.
Exactly. Also, it's quite warm at 20 degrees. I mean, finally, spring looks like it kicks in. It kicked in finally.
But the forecast is that the summer can be quite late this year.
Oh, really? Okay, then not an equally pleasant news, I would say.
Yeah.
Okay.
In the Netherlands, you never know what kind of weather you get.
I believe that's something I've learned pretty well on my machine in the past 1.5 years I've been here. So yeah, but that's also the beauty of it. So okay, I gave a small introduction about you before you were joining, and so just to recap, you have been doing your master degree in theoretical physics at the University of Amsterdam, right?
Yeah.
So okay, so that was your latest stage of academic degree, right?
Yeah, that was the last thing I finished during my academic career.
Okay, and the topic of today I briefly mentioned will be fluid dynamics, which I didn't really know much about, but I had indeed the chance to learn about. Toon did you did your master thesis in lava flow modeling, so we will be also covering going into that part. But I would say that to kick in, to jump into it, can you tell us what is fluid dynamics and how is it relevant to everyday life? Why should we care about fluid dynamics? Let's say.
Well, then the other question is, why shouldn't you care about fluid dynamics? Like you mentioned, it's kind of an obscure field of physics. I heard from some of my colleagues that it is due to some misconception that fluid dynamics seems to be finished, but there is still a lot to do. The only thing is, it's a very old field because it goes way back to early civilization, starting with irrigation. Well, because it's also a really practical field. You can do experiments and also do a theoretical approach.
Okay, but why do people say it is finished?
For me, that's also a good question because, apparently that's kind of a misconception. I did also a research project during my bachelor's at the Utrecht University, and that department of fluid dynamics was also fairly new, and the department at Amsterdam University was, I think, 1 or 2 years old at the time. So it's getting some sort of a comeback. Okay,
but that's strange because I also wanted to ask you I said to which other field when we were discussing about the topic you told me that there are many applications for fluid dynamics, for fluid mechanics, but then to which other fields can we apply fluid dynamics to?
One major field is, for example, civil. Let's see, I've written it down, so it's quite easy to remember.
Civil engineering, no.
Yeah, civil engineering. For example, how do you get water from, for example, a river to your house? And therefore, you have to use some kind of pressure to keep the pressure in the tubes at depth good level, so you get pressure in your house. And that's why you get some nice water towers in the Netherlands, which are quite old, and yeah, they are currently obsolete, but they were used in the past to really keep the pressure on the lines which were feeding houses with water. So that's already a big application of fluid dynamics.
Okay, so overall we can say that we civilians, people not interested into fluid dynamics, we can be concerned about it because we are touched upon by it.
Yeah.
Okay. Okay, great. So then let's dive a bit into the topics. What are some of its let's say cardinal main principles or equation that governs the behavior of fluids? How do these principles works?
Well, I shall share to you some material I prepared.
Yeah.
Makes it quite easier. So you can see this screen?
Yes.
Okay. Well, something to show you more about what kind of fields are there. I already mentioned, well, it's a very old field, which starts more or less with irrigation. And here you have a picture of a water tower from civil engineering. But fluid dynamics has also a big part on aerodynamics, because you want, for example, a plane which has a very low drag, so you can spare much fuel. And also another kinds of fields are, for example, star formation, where you can see fluid dynamics. Relativity is also a field where fluid dynamics is used. And you have also biology and planet formation. But you want to know about the equations, and it's more or less an approach on Newton's equation. So F equals ma, but then in its more continuous form. And then you get the very famous Navier-Stokes equations, and that's more or less this one here. And it's more or less an equation that explains everything for what the fluid is going to do.
Okay. So that's basically summarized in this equation.
Yeah, that's more or less the starting point when you start studying fluid dynamics. You get the derivation of this equation, and then it's more or less your holy equation. Every problem starts with Navier-Stokes.
Okay. Can I ask you? You said previously we can apply fluid dynamics to, you said star formation and general relativity. Can you touch very briefly in general relativity and star formation? How does it relate to these two topics? Because in my mind, which I tell you again, I had no knowledge in fluid dynamics. I find quite let's say unrelated. So things like fluids and general relativity and star formation. How do they are even related?
Well, it starts more or less with a definition what the fluid is, because maybe you can tell me what you think of what the fluid is. Start with that. Okay.
So, my definition of a fluid would be because that's also the thing. I have to start from the fact that the fluids are composed of molecules. Okay, so at the end of the day, they have the same, let's say, consistency of. They are made of the same building blocks as material concrete stuff is made. But why then does it have fluid properties? Well, yeah, that's a good question. I should take some time. But what is then the definition of fluid then?
A fluid has, most people think that fluids are more or less liquid. Everything that is liquid. But the pure definition of what a fluid is truly anything that can flow. So you have, for example, plasmas, which can act like a fluid because it can flow and move around in a volume. But water is a fluid, but you can even see sand as a fluid.
Okay.
So it has very strange definition, but it's more or less everything that can move by a certain force can act like a fluid. And then you are already in the field of fluid dynamics. And for example, in star formation, you have to deal with a lot of plasma and eventually charged fluids. And this is also incorporated in the Navier-Stokes equation. And this is one of the reasons why you can use it, for example, to model star formation or the explosion of a star, because it has a lot of fluid dynamics in it. And for relativity, you can, for example, in the old days, there was the misconception that there was some kind of ether. So that was already seen as a kind of a fluid. But nowadays, we already know that, well, the ether is just some bogus thing that it doesn't really exist. But still, you can use the Navier-Stokes equation to model, for example, you can see space still like some kind of fluid, because if you have, for example, radio waves, it needs some kind of medium to move through it. But doing so, it can, for example, move this medium, and it can still act like a fluid. So it's kind of a very deep field that has a lot of connections with other fields.
Okay, that's interesting. I didn't expect that. That's very nice then. Okay, do you have any other equation you can show us?
Well, yes, there are other equations, but they are all derivatives of the Navier-Stokes equation. But
So they are.
In fluid dynamics, you have the Navier-Stokes equation and also an equation that accounts for mass conservation. And these are just the main equations in the whole field. So you don't have a lot of equations to start with, but a lot of equations follow from this equation.
Okay. Can we say that fluid dynamics is, let's say, a subset of classical mechanics?
Yeah, I think so. Because the equations of Navier-Stokes follow directly from the Newton equations. For example, if you look at this term, it's more or less m times a, but here we have divided by the volume, so we get the density times the acceleration. So here you can also see that it has more or less a subfield, or it more or less follows from classical dynamics.
But Newton mechanics, from Newton we know that an object will keep on going in constant acceleration unless acted upon a force. So that's what Newton told us. But now I ask you, what are the things that exert forces on fluid, and how do these external forces, so these external factors as temperature or viscosity, how do these factors influences the behavior of fluids?
Well, let's start with an easy one. If you, for example, have a big bucket of water, then you have a big mass of fluids, and then you can already see, well, gravity is going to have a big part of the interaction of the fluid with its surrounding. Because if you drop the bucket, then the water immediately falls to the ground. But you can also have, for example, some kind of gel which has electrolytes in it, so it can it has some kind of effects following from electric or magnetic fields. So if you, for example, think about your tap water, it has some kind of ions in it. And there's currently also a method where you can just attach a magnet to your water line. And this, it more or less catches the calcium ions, so you get smoother water.
Okay. that's cool. Okay, I didn't expect this one. Okay.
Yeah, it's pretty interesting.
Okay, so many new things I get to learn. Okay,
but, to tell you a bit more about additional forces, because these are also incorporated in the holy Navier-Stokes equation. Because if I tell you something more about the terms, because you have, for example, this term, and that totally accounts for all the pressure inside of the fluid. So if you apply a pressure on the fluid, but the fluid can also apply a pressure on its surrounding. So this is more or less the pressure force.
Okay.
And here you force.
Sorry, you said the pressure. You said how do you call it? Yeah, it is the minus the Jacobian of. It is minus the Jacobian, right, of pressure, and the pressure is intended as pressure exerted on the fluid and by the fluid on its surrounding. Okay. Sorry, go on.
Yeah, you have also the electrical force, which is no, the electric force is this one, because you can have, for example, what you mentioned, water with ions in it. So it is it has a force component if you apply an electric field to it. But you have also a force due to the viscosity of the fluid. And I don't know if you know what viscosity actually means.
Can you explain it?
Yes, I have.
I ask you like I do to ChatGPT. Can you explain me what viscosity is like if I was 10 years old?
Well, viscosity is more or less a value attached to, which is more or less a fluid property that tells you how easy it is to deform the fluid.
Okay.
And if you, for example, look at this figure, which you can find on Wikipedia. So here you can see two kinds of fluids, where this one has a high viscosity and this one has a low viscosity. And if you see how it flows, you can see that the one with high viscosity deforms much less than the one with low viscosity. So it's more or less like it tells you how much the fluid resists deformation.
Okay. Okay. So, if I understand correctly, is it okay? So a high viscosity fluid, so as the one on the right, will be less, let's say, less easy. Yeah, yes, less easier to manipulate.
Yeah.
To deformate. Okay. But what I think, my intuition now that you just explained this would tell me, okay, the fluid on the right is more as a higher index of viscosity, but I do see it because the other one is basically just, let's say, water, pure liquid. But if I try to manipulate, if I try to deform the high viscosity fluid, my intuition before you told me that was that, okay, that liquid, that fluid is more compact than water. So deforming it into a shape or into, I don't know, restraining it to an area is easier because it, let's say, it does not, let's say, doing it saying the same with water, it's impossible to restrain water with your hand only because water would, I'd say, cover all of your hand around. If you can do that with a high viscosity fluid, I thought, okay, maybe I can, I'd say, that does not flow all around my hand and all inside the cavities of my hand. And so I can make it, I can manage to, I'd say, catch it all without letting it flow, even, let's say, spill it over any other part. Why is my intuition wrong?
Maybe can you make your question clear, because I don't really understand what you're.
Yes. So basically, you said that a high viscosity fluid is more difficult to manipulate. Let's say, right?
Yeah.
Okay. So we know that now the orange fluid on the screen has a higher viscosity level, and so it is harder to manipulate. But what my intuition, when you just showed the animation and said that the one on the right has high viscosity, I thought, okay, then higher viscosity means it is easier to manipulate because it's okay. Let's say it brutally. The fluid on the right looks more concrete, looks more compact than water, which is, let's say, purely liquid, which I find it very difficult to grab and put it somewhere else or restrain it to some area of the box, for example, because water flows all around my hand, whereas the viscous fluid, it is more compact. So it is, let's say, quote unquote, resembles more of an object which I can take entirely without pieces of it spilling over my hand, or I mean the thing I am trying to restrain it with. Is it more clear?
Yeah. So what your intuition is right. It's easier to change the shape of a high viscosity fluid, but then you also have to apply much higher forces, because the fluid is also more exerting a force against you, because it doesn't want to deform that much.
Okay.
So
Okay.
it's both are true. So high viscosity is easier to manipulate, but you have to use much bigger forces to truly manipulate it, because it also has some kind of resistance against manipulation.
Okay. Now I understand. Okay. And so, do you have any other, let's say, properties regarding fluids that you can tell us about? Because I wanted to, when I was reading about fluids, I read about turbulences, which intrigued me. But if you have any other properties you want to firstly explain, then go ahead. Otherwise, we'll ask you about turbulences.
Well, let's do then turbulence first, because that's more or less an easy part.
Okay.
Well, then you have to start with what is the Reynolds number, because the Reynolds number really tells you what the fluid is doing. So if it is, for example, laminar fluid or turbulent fluid. And laminar fluid is, you can look at this image, which tells you pretty much what laminar actually means. For example, a laminar fluid has a very low Reynolds number, which means that it has a very high viscosity. So it's probably very slowly flowing through, for example, a pipe. And then you can exactly, for example, see that the fluid is built up of layers. And each layer has a constant velocity. So if you have, for example, this pipe, then you can say, well, for example, there is a high resistance at the wall of the pipe due to some microstructure and it's not really smooth. And then you can, which is more or less one of the boundary conditions I will tell you about more later. Because at the walls of a tube, you can, for example, have, the fluid is flowing here, so it has a non-zero velocity component, or it really sticks to the wall, and then it has a zero velocity component. And for laminar fluids, it's more or less like the pattern of the velocity follows a parabolic profile. So you have a high velocity in the center of the tube and a very low velocity at the walls of the tube. And for turbulent flow, it's truly different, because for turbulent flow, it's more or less happens mostly in fluids that have a very low viscosity, and then you can think of water. And as you already mentioned, what your intuition is telling, water is very easy to manipulate, but it has a very low viscosity, so it doesn't resist that much deformation. So really anything can happen. So your velocity profile, you can't really tell anything about it. It has no kind of mathematical description that follows, for example, a box profile or a parabolic profile.
Okay. So basically, low viscosity fluids have higher chances, or do get a rise to more likely to turbulences.
Yeah.
Okay. What's let's say, can you make some examples of where let's say turbulences applied to fluids in real life can make things go very, very wrong?
Well, turbulence is the one major thing that you want to avoid when you're, for example, transporting oil through a pipeline. Because you want to have it very quickly from one end to the other. And due to turbulence, you can get very high resistance due to wall, or it even can be the case that the fluid is, for example, it has internal friction, and then it can heat up and become more fluid.
Sorry, what do you mean with the fluid having internal friction?
Well, here you have for laminar flow, you have just layers that are just slightly how do you say it, sanding each other. So they have some kind of very small resistance between layers, but in turbulence it goes always. So the fluid flow can, for example, go this way or that way. It can even follow some kind of whirlpool motion. It is just some completely random motion that's happening inside of the fluid, and that can result in some very high frictions. And it's not really a good thing to have when you want to transport something in a pipe from one end to the other, and in some kind of time frame. And it's also very difficult to predict or even say, well, we have some kind of friction there, what's happening over there, and can we describe it? Because turbulence, it's really a field where you, it's just one phenomena that you want to avoid.
Okay. Firstly, I believe with regards to example you made of, for example, oil in a pipeline, like is the consequence of turbulence is going terribly wrong. The fact that, for example, within a pipeline we may have a loss of the fluid, or that gets somehow stuck.
I think a better example is, for example, airplanes, where you have also the term turbulence. And then it's more or less like, well, you want to make your plane as smooth as possible, so it has very low resistance to the air. But due to turbulence, you can get a very shaky plane, because the flow is not laminar anymore, and there is some kind of, for example, some kind of void happening outside of the plane that really, for example, it creates a very locally low pressure region. So if you see, for example, over here, if you have laminar flow and you have some kind of object, for example, with a very sharp edge, you can see that it might happen that here some kind of swirling motion is going to happen, and that's turbulence that you want to avoid.
Okay, so basically, if I understand correctly, turbulence is also mainly involved with regards to the, let's say, to the flow of the liquid per se, with the risk of damaging the liquid. Because if I make the analogy with the airplane, you have turbulences. It's not that something spill over or whatever, but it is the airplane per se which can get damaged. So I believe that same should apply to liquids then.
Yeah.
Okay. Oh, that's very that's very interesting to say. I've never actually, to be very honest, I never thought of fluids this way. I always thought there were, I would say, some abstract entities, very abstract to manipulate, or God knows what formulas were behind it. Okay, and
there is not really that high of an abstraction in fluid dynamics, because you can, for example, make a model, but if the model doesn't work, you can always go, for example, to a laboratory and do an experiment. That is a nice thing about fluid dynamics. You can test it both ways. You can do a model and you can do an experiment, but at the end of it all, they both have to match.
Okay, you just now mentioned a model, but then I ask you, how do we? Because you provided some equation, some principles behind fluid dynamics, and then you gave us some examples. But now I ask you, how do we mathematically model the behavior of these fluids, and how, let's say, what challenges do we face when modeling these dynamics?
Well, let's see. Modeling of fluid dynamics, yeah, it has a big branch in software, which is called computational fluid dynamics, which is shortened to CFD. And that's more or less the part of the software industry that focus solely on fluid simulations. And you can, for example, make simulations of a sphere, which you can see over here. And then you have some kind of fluid that's going to flow from this side and goes to that side. And then, you have two main principles. You can, for example, take an Euler approach, and then you divide the whole domain in, for example, squares or triangles. It really depends on the software, or if you build it yourself, you can choose the shape you want, and you make the whole domain discrete. So it's the whole domain exists out of tiny triangles or large triangles. It just depends on the case you want to compute and what your main objective is.
Okay. What are some challenges when modeling fluid, when mathematically modeling fluids?
Well, one of the main issues, which in real life you also want to avoid, is, for example, that you get turbulence in your model. That might happen.
How do you have turbulences in your model?
Well, it depends on your fluid, the velocity of your fluid, because as you can see over here, you have laminar flow, but when it passes over this circular object, you get to see here some swirly motion of the fluid. And if you take fluids with decreasing viscosities, because this Reynolds number increases, so then you already see, well, my viscosity is so decreasing, then you can see that this field, it's getting larger and larger.
Okay, wait a second. So in this sequence of images, we are seeing viscosity increasing.
Yeah.
Okay. Wait a second. Intuitively, how do I explain? How do you say? I cannot grasp the intuition. Why do we have more? We have more turbulences the higher the viscosity level? Because what I would think is it is that a low viscosity liquid fluid is, easier, let's say it brutally, to spill around, to mess up. Okay, whereas a higher viscosity fluid has higher traction. Sorry, higher friction, meaning you need to put more force in it to modify it. But then, how does it? How can it be then just rising the viscosity leads to greater turbulences? At least in this case, maybe it is very dependent on the case.
Well, it's not a rise in viscosity that leads to turbulence, but a decrease in viscosity, because the Reynolds number is more or less the velocity of the fluid divided by the viscosity.
Okay.
So your viscosity decreases, your Reynolds number increases. Okay.
So then it matches with my intuition. I guess. Yeah. Okay, I understand. And so that is mathematical with regards to mathematical modeling. But do we have, or at least, can you make some examples of where mathematically modeling fluids and fluid dynamics has been finding some practical application, and it has been of real world based use?
Well, I already mentioned it. For example, aerospace. In the early 1900s, when the airplanes just came to be, well, it wasn't really known how to make a perfect plane with very low resistance. And due to into the 80s, when all the CFD software was more or less getting better and better, you could really make a model and really fine-tune your airplane. So, yeah, you could really display the drag of the air on the plane. And you can also do it practically, because you have, for example, here a car. And in the wind turbine, you can also model the drag resistance by using some kind of smoke, and then you can see that the smoke passes over it. And when the smoke is doing something just completely random, it's even creating vortexes, then you, for example, see, well, this part might be caused of this turbulence, and that might increase your fuel consumption when you're driving. And you can even use mathematical modeling of fluids to, for example, if you, for example, have some kind of oil spill, then you might have a question, well, how is this oil spill gonna evolve into the sea? And then you can, for example, have this kind of model. I can make it bigger. So you have some contamination in a river, and then when you model it with CFD software, you can see that it starts to grow. And then you can, for example, make some kind of countermeasures to really encapsulate this contamination.
Okay, so basically when we hear about pollution disaster of container ships containing oil, you are not interested into the environment per se. You're only interested in how you could have prevented it through fluid modeling, right?
Yeah, because there are some. There's always you always want to avoid it, but if it truly happens, you want to know, well, how can I prevent some further damages to the environment? And then you have to know, well, how is it going to develop in the water? And nowadays we also have the issue with global warming, so rising sea levels become important. And in the Netherlands we have the dikes. And then we can, for example, use some kind of CFD software to really model well how high must the dike be, how much force does it need to endure when the water level is going to rise. And then you can, for example, make some kind of model that says, well, our dike has to be so tall and this broad, and it has to be made up of mostly it's just dirt that it's made of, but you can, for example, mix in stones or other kind of stuff to really make it very structurally sound. So it can support a lot of it.
Okay. I also see in the slides you prepared on the lower right corner, that is Venice. We are in Italy there. Why is that?
Well, in Venice, they have currently an issue that the water level is so high that, for example, the plane near the San Paolo Basilica, I think it is. Well, the whole plane is just
San Marco. That basilica is San Marco.
Oh, San Marco, yeah, the San Marco plane. Well, the whole plane is just going underwater. And they currently have some kind of defense system against this water rise, which is a flexible dam that they can put up or put down.
It's called I know about this because sometimes I would see some articles in Italy. It's called the Moses.
Yeah,
that's the name. That's the name of the thing. Okay, and also I believe that is as you said, that is a construction purely based, actually purely the result of what you said, fluid modeling.
Yeah, and in most cases, it is built by a Dutch company.
Which one? Which one? We do not want to make from.
Well, there are some very huge global structures made, or for example, those islands near Saudi Arabia, those big palm trees. Those are made by a Dutch company because we are because we had to fight against the water. We are really good at predicting how water is going to flow and what we have to build to prevent any kind of water spilling.
Well, to be honest, I think it makes sense that the best in the world at making dams are the Dutch. It's like literally the population who built a country from underwater, basically. So.
So if there is some kind of water involved, because a few years ago you had the Hurricane Katrina near New Orleans, and then some Dutch company had to go there, for example, to tell, well, how do you need to build strong dikes and how do you do it? But that's
pride.
Yeah, Dutch pride, Dutch expertise, but it's also one of the big civilian engineering projects you can do with fluid dynamics. Just keeping the water out.
Okay. That's. Well, do you believe that the Dutch got so well at doing this because of let's say natural selection? If they wanted to build their country, they had to get good at this.
Yeah, we have I think 400 or 500 years of experience at least.
Okay. That's very nice.
Yeah. Yeah, but another kind of fluid dynamics, I already mentioned, you can, for example, explain how pollution is going to move inside of a body of water. But in the corona times, you also had the issue that the coronavirus was going into the groundwater. That was also a big issue at the time. And with fluid dynamics, you can, for example, also make a model where you just put some particles in a fluid and make some tiny surface that is, for example, existing out of ground, which has tiny channels in it. If you zoom in very highly, then you can, for example, model how this contamination of the coronavirus is going to move through the soil into the groundwater.
Okay. Well, I've never heard of modeling a coronavirus within fluid. That is really new to me.
Yeah, that was due to that was during my research project at the Utrecht University, where Corona just it just happened, and I had to graduate my bachelor during the startup phase of the Corona, and then I was modeling tiny particles in for example, soil. And one of the main questions during my research was, for example, can you model the spreading of the coronavirus in groundwater?
Okay. How was it complicated?
Well, I didn't get that far.
Okay.
The fluid dynamics software, you have, for example, commercial packages, but you also can write it your own. But it totally starts with understanding how the software is going to act. In some cases, you have software where you just plug in equations which depict the forces, but then you still have to know how the software is going to, for example, incorporate those equations into your simulation. That's also one of the tiny difficulties that you have to go over.
Okay. You mentioned before boundary condition. That we would touch upon later. And now I would like to ask you, what do you mean with boundary condition? And by reading a bit to prepare for this episode, I read that boundary condition and external forces can affect the fluid, the flow of fluids, and so I would like to ask you, yes, mathematically they will have their meaning, but how do we incorporate these effects in our model?
Yeah, one of the major boundary conditions when you're modeling flow in for example, a pipe, you have to always think about, well, what is my velocity of my fluid going to be at the wall? And then you get, for example, the no slip or the slip boundary condition. And you also have this in physics, where you have, for example, a bouncing ball. And if it bounces back if it bounces at the wall, then you can, for example, also make the assumption, well, the ball is not turning, so it really stops when it hits the wall. Then you have a no slip boundary condition because your velocity is 0 at the wall. But it might also be the case that it, for example, is maybe a little bit lubricated, so it can rotate when it hits the wall, and then you have a slip boundary condition. So those are one of the major boundary conditions when you're modeling fluid dynamics. Is my velocity 0 or is it non-zero at the wall?
Okay, how do we take into account of this condition during our modeling, let's say, part, so into our models?
So really mathematically incorporating it in your model, or how do you exactly want to know it?
Yeah, so how do you say, let's say, how can you adjust your model in order to properly account for, how to say, the boundary condition that you may face during real life, I'd say, examples? So yeah, I think I mean mathematically, of course, within our simulation, within our models.
During your modeling, you're most of the times creating solutions for the velocity of the fluid. And then you, for example, can say, well, my derivative of the velocity at the wall is, for example, 0, non-zero. So we have an acceleration or not, which really tells you, well, for example, my velocity is non-zero or 0 at the wall. But you also have a spatial derivative, because you can, for example, say, well, the derivative of my velocity in the y direction equals 0. And this more or less tells you, well, that the velocity doesn't change. So you can set it to 0 or 1 or anything. So it's a slip boundary condition.
Okay.
So it really depends. If you have a no slip boundary condition, then you can say, well, the velocity derivative in the x or y direction is 0. So it's a constant, so you can give it a value. But you can also directly say, well, my velocity is just 0 at the wall. And then you have a non-slip boundary condition.
Okay.
So it's mathematically, sort of easy to tell your software, well, I have slip or non-slip. But if you have a slip condition, you have to define what your velocity is going to be. You can, for example, also plug in some kind of weird slip velocity profile that depends on your position.
Okay. So overall, taking into account of this slip boundary condition is not challenging.
Yeah, it's also in fluid dynamics. You can also, for example, when you have some kind of issue, you can just say, well, I have a model. What the results are telling me, it's not really physical, but my solution doesn't work. Then you can also say, well, I'm just going to try everything. So you get very creative with your solutions, and at some point you might even find a solution, but then it becomes the question, well, is it truly physical what my solution is?
Okay, and how do you determine that?
Well, first of all, the major thing you're going to do is when you have found a solution by just trying everything, you just look at the behavior of the fluids. And I have an example of this which I had during my research. I think it's this one. Because I was modeling lava flow and I was just interested in, well, if I have two domes, which are here the left side and the right side, then if they are fusing together, I was expecting, well, this dip might occur. And then my question was, can I get some kind of mathematical description that tells me the behavior of the dip during time? And one of the issues I had was when it was trying to merge, you got this strange behavior over here. So I will make just a little bit larger so you can see it better. So you can see this weird behavior happening.
Mm-hmm. What does that represent?
Well, this is just a blob of fluid.
Mm-hmm.
And it collapses due to gravity. So it's a rather simple model of when you have some kind of dam that is keeping the water inside. Well, when this dam breaks, what's going to happen to the flow? How is it going to flow over the surface?
Okay, and what is the anomaly behavior we can see on the right?
Yeah, that was a big question. Because what this model was more or less telling me, well, your two blobs of fluid are never going to merge, because this void over here was telling me, well, there is some kind of air pocket that keeps your fluid from fusing, which was really strange, because if you have some kind of feeling in fluid dynamics, you can really say, well, it's very strange that this is going to happen, because when you have just two drops of water and you put them close to each other, at some point they are going to merge and there's not really any kind of division between them.
So how is it possible, at least if you know by now, how is it possible that is happening in your simulation?
Well, in this simulation, I had to allow the fluid to have some kind of slip condition at the wall, because otherwise it would stick to it. And you could get some really weird behavior where this fluid is just going to hover above the surface. So that was one of the first fixes I had to do. And another fix was because of this, because you see here that this blob is attaching through to the wall. And this was telling me, well, it's going to merge, but some kind of air pocket still remains, which was kind of strange. And I tried different solutions, and yeah, one of the solutions I tried was, just a creative solution. When the fluids are some critical distance away from each other, then I'm just going to force the merger and just look at, well, what kind of behavior am I seeing? So that was this solution. And then you can see after some critical distance, I force it, and then you can see this happening. And maybe it's a good question for you. Do you think this is really physical, that it happens this way?
Well, because I would say if you forced it to be the case, then I would say no.
But what if I tell you that maybe the time of fusion is very, very small?
Sorry, repeat that. What if you said?
What if I tell you that, for example, the time of the fusion might be a millisecond or a nanosecond?
Okay, then yeah, okay. It may be feasible, but how can it be?
It's a tough question. But yeah, coming to the point of this result, well, it's more or less gives some kind of behavior that matches the original figure, because the first one showed the blob at the wall. And here you have still some kind of merging where I forced it, but there you get this air pockets, and yeah, it's kind of a strange behavior if you really look at it. Because it just smashes at each other and the air pockets remain in it. So it becomes stationary. And
Okay, is this behavior, how do you say, is the fact that the air pocket is bigger here, is this due to the fact that you forced the fusion between the two fluids, right?
yeah.
Okay, okay, but so basically, when you forced the fusion between the two fluids, you hope that the weird behavior of the air pocket that you showed on the left would disappear.
Yeah.
Okay, but then you saw that it just got bigger in a second.
Yeah.
Okay, that's
it's
great.
just like when you have two bodies of water and they collide with each other, then you really expect, well, at some time, all the air between the collision is just going to go up through the water and just going to the air again. So it becomes truly a solid block of water. That's what you might expect when a fusion is happening.
But instead,
But instead, during my simulation, the air pocket remained. So that was a strange behavior.
how did you went around it?
This solution was just, what's going to happen when I force it? Is the air still going out of the fluid? But it didn't happen. So then I looked at my boundary conditions, and then I saw that this one was more or less a good solution, because you don't see any kind of air pockets, only this one. But after some time, it might just go through the fluid and go outside. So this was really a good result. But one of the major things I used for that is that I allowed my fluids, and in this case it was the air, to have I named it a vertical slip condition.
Okay, what do you mean by that?
Well, a no-slip condition at the walls here tells you that the fluid can't really move up or down.
Okay.
But when you allow for it, then this air can completely go out of the fluid and you have full merger.
Okay.
So it's more or less, when you have a wall, you have always the question, well, is my fluid, for example, have a velocity component in the X or Y direction, or only in the X direction, only in the Y direction? And at some point you can always, because you're using a model, you can always try different approaches. For example, try an X or Y velocity component, try only an X velocity component.
Okay. What I really like about fluid dynamics for what you have been telling me, and in particular the modeling aspect of it, is that there appears to be sort of a synergy between as you said, practical experiment and simulations. Like they do appear to work together. You can combine them and extract insight in both from both cases. Whereas I literally can think and name many other branches of physics where you cannot test, you cannot have experiment. Either you go on purely theoretically, or pretty much that's the only road you can take. I only have to mention, for example, like something like string theory or quantum gravity. We cannot test those kind of stuff, and so this is actually very practical, very handy. I would say that it comes that it boils down to.
Yeah, and it's also very intuitive how you, when you know the formulas, and you can you can really make some experiments even in your head. For example, say, well, my fluid is very viscous, then my Navier-Stokes equation is going to look like this. And then you have, for example, an analytic solution you can try. And
Okay.
yeah,
You make a Gedanken experiment, like Einstein would call them.
yeah, but you can already go to the lab. For example, if you go just a simple solution, looking at the Navier-Stokes equation, and you have this Reynolds number. For example, if you have a very high Reynolds number, you can say, well, my viscosity is very low. So you can say, well, this term becomes much smaller than this term. And if you have a fluid that has, for example, a very high viscosity, you can totally neglect this term. And you get, for example, Stokes flow. And Stokes flow, which has an analytic solution, you can already model. And this is more or less the solution for Stokes flow.
Okay, what does it represent specifically?
This is a pipe.
Okay.
And the color represents the magnitude of the velocity.
Okay.
So if it's the red color represents a high velocity and the blue color represents a very low viscosity. And the fluid is entering from the left side and flowing to the right.
Okay.
And this is one of let's say one of the few analytic solutions you can find for the Navier-Stokes equations.
Okay. So I am lucky I can see it right now.
Yeah. The beauty, the strange thing about the Navier-Stokes equation is you can model, more or less any kind of fluid, but finding an analytic solution for the fully Navier-Stokes equation, it's still not found yet.
Okay. So we may we may have to talk to make another episode when it will have been found, and we.
Yeah, that might be a long time because it's a very complicated equation. It looks simple, but it's really complicated. I think it's until now still one of the millennium issues that you can try to solve and win $1 million.
Oh, really? It isn't the millennium problem?
Yeah.
Let me search it. I didn't know. I knew about the more classical, let's say, problems like Riemann hypothesis or P versus MP. I didn't know the Navier-Stokes equation was in there. Oh, that's very interesting. We may we may want to spend some time on it. Yes, it's actually right. Yeah. Navier-Stokes existence and smoothness. Yeah. Okay, so great. I know I can. I will start spending some time. Road to the 1 million. Okay.
Well, good luck. I think many.
Okay, listen, Ton. I wanted to ask you. You said you have been modeling. You said before you have been modeling lava flow for your master thesis. Now I want to ask you. Yeah, we all know how lava flows pretty much. I'd say we know how does it work. We have seen volcano erupting either on the internet or whatever. And I want to ask you, how does the consistency of the ground, so it's called the topography, influences the behavior of lava flow?
Well, that's a good question because there are two approaches for lava flow. One approach is, for example, that it is a Newtonian fluid. So it's just a fluid with a very high viscosity. And I can show you some kind of models in fluid dynamics that exist. So here are a couple of examples of different models of fluids. And here this straight line here is a Newtonian fluid. And this model tells you that if you apply some kind of force, it's going to deform directly. So it has a direct link to, well, if you even exert a very tiny force, it's already going to deform. But another approach of lava as a fluid is, for example, that it's a Bingham or even a Herschel bulky fluid. And these kinds of fluids are very strange because they can act as both a solid and as a liquid.
How does that work?
Well, it totally depends.
sorry. This reminds me of of in quantum mechanics when we say a particle can be a particle, but it can also be a wave. Yeah, shut up. Okay,
well,
so you were saying.
That's the quantum mechanics issue, but in fluids, it's more or less like you can, for example, think about toothpaste. Because toothpaste, when you don't exert a force on the tube, it stays inside of the tube. But when you exert enough force on it, it flows outside of the tube. So when it's in the tube, it more or less behaves like a solid. But when you apply a certain amount of force, it behaves like a fluid and it starts to go out of the tube.
Okay, so in this case, what do you consider the toothpaste to be? Both or as a fluid or a solid?
Yeah, during my master thesis, it was actually both.
Like quantum mechanics.
Yeah, but quantum mechanics say it can act like this and that. So it's more or less like, well, it is both a photon and a wave at the same time. But in fluid dynamics, it doesn't have the behavior of a solid and a liquid at the same time. So that's a major difference. Because at a certain time, you, for example, don't exert a force, but when you start to exert some kind of pressure on the tube, the force increases in time. And after a certain buildup of force, you get some kind of boundary which you go over, which is called a yield point. And after this yield point, it acts like a fluid. If you understand what I'm saying.
Yeah, but what I was, I do. Yeah, this struck me, but because I was thinking about. So basically, you said that in this case, toothpaste can be the same, can be both things at once, can be display both behavior at once. But and you said for just enough force that I exert on the tube. But now I think, okay, let's try to pick any other very solid and concrete object, which and now, like for example, beside me I have a little lamp, which I say, okay, within this tube there will be, let's even say there will be a wire. I don't know if there is, but I suppose let's even say that there is a wire. If I start pressing here very, very strongly, or on the other side or whatever, very, very strongly with enough force, won't I obtain the same effect as with the toothpaste, so that the wires will start then flowing away, flowing off this tube. And then I say, okay, but like if I think about it from a theoretical perspective, then I don't really care about the mass, the force that I apply in it, because I can say whatever mass it's needed, I can apply, I can use it. But then if the wire really comes out flowing from the tube, then do I have to say that the wire also behaves as a liquid, as a fluid?
Yeah, I think the major difference is that you, what you already mentioned, you can apply a certain amount of force, but then you can get plastic deformation, and the other one was, well, it's more or less a different. Yeah.
So sorry, I want to say very quickly, don't you get plastic deformation even for the tube of toothpaste?
Yes. Yeah, it's a very strange behavior of fluids that apparently exists.
Okay.
It still vexes me that a fluid can be both solid and liquid at certain amounts of time when some sort of force is exerted on it. Really strange if you look at it, because there's also still a discussion about solid glass, for example. When you go to a church, you can see that the panes of glass at the bottom are thicker than above it. And then you can, for example, also make the assumption that solid glass is a liquid. And I'm not really into it, but I think there is still a huge discussion what glass really is. Is it a fluid or is it a solid?
This is what in a nutshell what physicists spend their time on.
Yeah. Discussing all kinds of topics.
Relevant and irrelevant.
It always comes down to, well, if you make some kind of assumption, and at the end of it, does your assumption really help you to explain the behavior what you're seeing?
Okay.
That's also I think a major big part of physics. You make an assumption, do experiments, or even use mathematics to come to your theory. And then you can look at, well, is my theory predicting what I was assuming that was going to happen?
Okay. And then came Gödel 100 years ago, saying that we cannot prove every statement within a formal system of axioms. Thank you, Kurt Gödel.
If you're using pure logic, then I think it was also, maybe it was Gödel, yeah, that he said that, well, you can go from A to B, but if your assumption is right, you also have to go from B to A again. But in some cases, from going to B to A is, it's going, not actually going as planned. Know how to go from A to B, but going back again using some kind of logic, then it becomes very difficult.
Yeah. Okay. So interesting, very, very interesting. I believe all this. As well, many, I would say, I would say peculiarities that one can wrap his head around that I didn't know about it before. So it's very interesting. And as a last thing, I would like to ask you if you can tell us a bit about let's say the current challenges that research are facing in fluid dynamics research, and lastly, if let's say there are, let's say in the short term, let's put it this way, in the short term there are any major breakthrough that we may be able to assist.
That's a good question, which I really had to think about, because as already mentioned, there is some kind of misconception that fluid dynamics is more or less finished, and all the research groups I went to were most of it was new. So I think still there is a lot to do with fluid dynamics. Currently, you can also apply fluid dynamics in the semiconductor industry, which is going in great steps to even increasing smaller size of chips. And I had also one of my one of my other colleagues, which was studying the deformation of bubbles in viscoplastic fluids. So these are the kinds of fluids that act both as solid and liquid. He was trying to model, well, how is a bubble going to deform when you apply a certain amount of force to it? And this might lead, for example, to a new kinds of mayonnaise, which is just a fluid with bubbles in it. And then if you really look at it, you can see that it's more or less a viscoplastic fluid. So this is one funny example I could think of. Maybe some new kinds of mayonnaise.
which is at the end of the day, it is a major breakthrough that we can assist during our life.
But yeah, other kinds of breakthroughs I was thinking of was maybe in on the area of software, because modeling fluid dynamics, if you truly want to match experiments, you have to use very fine discretion steps. So very, very, very small regions where you divide your fluid within your simulation. And then it becomes very computationally heavy.
Okay.
I followed one course during my master's thesis, which was about star formation, where they used fluid dynamics to model star formation. And he had a movie of, I think it was 18 seconds. So it was 18 seconds, but he only got that movie after, I think, 8 months of computing using 10,000 cores or so.
No.
Yeah, it's truly very computationally heavy.
So also not even, let's say, not even that satisfying. Like you work 8 months to produce an 18 seconds clip. After 20 seconds, not even is already done.
It's for example, for easy problems, you can, for example, say, well, I'm just going to try a solution and maybe it has to run for a week, but I'm fine with it because I can always try again. But if you have very heavy simulations that take 8 months, you really have to think about, well, what am I going to do? What do I want to model? And then you start your model, and then you truly have to wait 8 months, and then hopefully it gives a correct description what you think is going to happen. It might also happen that after 8 months it gives completely bullshit.
And then you have to wait another 8 months, and then retry it again. Great.
Yeah.
Okay. So, but yeah, very interesting. I believe I am, to be very honest, I am most looking forward for the new type of mayonnaise. So.
Yeah, me as well. There is also some guy at Amsterdam University that's currently modeling algae bloom, because it's getting warmer due to global warming, and then you get very quickly blooming algae, which are it is really toxic to humans and animals. And now he's trying to find out some kind of method, for example, stirring some kind of stirring issue where you can, for example, break up the algae so the bloom stops and you get clear water again, because in the near future we might run out of drinking water. So the available drinking water, you want to keep it clean. And if algae are blooming, you can't really use it as drinking water anymore.
Okay. Very last question, then I leave you go. What do you think? Because you just mentioned about drinking water. Do you think that we may have some discovery in the short term with regards to a process found with regards to desalination of oceans or seas, so that we would basically just find an immense, a huge reserve of drinkable water? Because I know that there are some processes at the moment that have been implemented, but they are terribly expensive. They clearly are not functional for even the poorest countries to adopt. So do you believe we may have some progress in that side?
So getting more available drinking water in the near future.
Yeah. At least through desalination. Through the desalination of oceans and seas.
Yeah, I think desalination is already a good thing that you can do it, but as you already mentioned, it's quite expensive because you have to use I think it's very large machines, and you have to use loads of filters to really filter out all the salt. Yeah, but another method is, for example, boiling it. But yeah, I'm not really sure how they are going to solve it, because at the end it always comes down to, well, how much is going to cost? How much is the solution going to cost us? And I think that's one of the major things that's really keeping us from really going forward. It always comes down to who's going to pay it.
Yeah, which is unfortunate sometimes.
Yeah,
but okay. Yeah, so I think that was it. Thank you very much for this conversation, Tony. I think we can wrap it up here. We had quite a lot we have discussed on, and I really liked it. Thank you very much. I think it was very interesting to find out about all this stuff, which again I really had no clue about. So that is always great to hear and learn something new.
Yeah, hopefully it also helps to increase the enthusiasm for the field of fluid dynamics.
Yeah, so hopefully someone watching this episode may turn their studies into fluid dynamics. And we don't know. We just hope that is the case. But yeah, I think that's it for this episode. Then thanks to Ton, and thank you everyone to whoever is listening. And I will see you in a later episode. Bye.